My name is Professor Joseph Wunderlich. I'm Professor of Engineering, Architecture, and Computer Science. And this is a lecture on computer performance and five different things to take a look at. RISC versus CISC, the time it takes to execute machine instructions, assembly language instruction, Amdahl's law for speed up, law of diminishing returns, marginal returns, and how that could possibly be overcome now, theoretically. Then some mathematical models of speed up and some common benchmarks. Now, it's not spelled out here specifically. They refer to these high-level language computing architectures. Traditionally, it's CISC, C-I-S-C, for complex instruction set computing, versus RISC, reduced instruction set computing. So I'm going to say that and refer to it that way. Now, complex instruction set computing has many more instructions, fancy addressing modes for where the operand data is and all the instructions. I won't get into the details of all that. You take other advanced courses with me to discuss that. Reduced instruction set computing came about, several decades ago, actually a long time ago. I remember when it was, but it was based on the idea that most programmers, most compilers and operating systems didn't make use of the complex instructions, and so there was overhead involved in that. And then, so they just reduced the number of instructions and just left the ones more likely to be used. However, there were other things that went along with that, and in more advanced classes we'll talk about that. There's a thing called an instruction format, where you lay out the opcode that tells what the instruction does. This is machine language, which is a direct one-to-one correlation to assembly language. And then there's operand fields, which determine what the data is, if it's embedded right in the instruction, or where to get it. And there's a variety of places you could get it. We won't discuss here. Now, those fields were variable depending on the instruction. The actual length of the whole instruction was variable too. It's faster to have fixed fields in your instructions for execution, for decoding. The machine can begin to immediately go fetch operand as soon as it sees the opcode and knows right where the opcode is going to be. It's a fixed set of bits. In IBM, we had a big complex machine with a complex instruction set, so we had actually some bits that say, go get the rest of the opcode somewhere else. It was that big because we got up to 1,400 instructions when I was there. Typical Pentium families with the Katami extensions around order of magnitude 600-700. Microcontrollers are around, started at 100 up to 200-300. Simple microcontrollers like a PIC or 32. You can't do much with anything less than that. But anyway, so there are other things that came along with RISC other than just reducing the number of instructions. It would certainly be just a little essay kind of question if I ever asked you here, but it probably is more detailed than I want you to know for this particular course. There are other things that happen, the hardware control or the hardwired control unit in the CPU versus a programmed in nanocode. Don't want to get into that in this course. The control unit that controls the data flow, or something, the finite state machine that we discussed in 332 class, the Digital Design 1 class, we designed that, is hardwired instead of microprogrammed in the RISC. Also, you have more registers in the RISC instruction set, and you make use of them with a simpler instruction. So RISC, R-I-S-C, comes along with a number of things other than just reducing the number of instructions. And then we're not going to talk about the history of ARM. This is a summary sheet from the parallel processing textbook that you used in graduate school. Don't strain your eyes trying to read everything in it. However, I have the next slide. Made this a little easier to read. So this is CISC versus RISC. So CISC is a complex instruction set computer versus RISC. And most chips nowadays are, or well, had been RISCs. They steadily build more and more complexity in it, approaching back to the CISC processors. Originally, the idea was to reduce the number of instructions in the instruction set, equivalent to assembly language. The compilers compile down into machine language, and assembler assembles directly into machine language one-to-one. Those instructions, it was found that most programmers didn't use all the complex instructions, so the idea was to make a simpler instruction set for speed up. However, there are other things that came along with that. So you can see, read these things here, and I'll just read the ones that I have highlighted here. In the control unit, in the CPUs, the cores, the sequencer that executes the machine instruction cycle, the pipeline stages, pulls all the strings in the data path. That can be either micro-coded or hardwired. Micro-coding means it's programmed separately. It has its own little sequencer. Each instruction has its own little sequence programmed, and there's a finite state machine just for doing that. There's microcode, actual nanocode, very complex thing. Inside IBM, we had that for the large-scale systems because they were CISC, and you wanted to be able to change instructions over time and even put in a patch on $1 million machine somebody bought 10 years ago, update the instructions. So if they're micro-coded, which they can be in large systems in CISC, then it's slower because you have to interpret all that. If it's hardwired, it's going to be faster, as you see over in the CISC. You also have long microcode for complex instructions that takes up area, space inside the control unit. It's easier to program CISC because you have more powerful instructions, and you have lots of powerful addressing modes, so you can do all kinds of things. But you may not use those instructions. So the RISC is good for pipelining. Also, the hardwired controls faster, although it may have more code and may be harder to program. You don't have the fancy instructions. And easier to match your clock cycle to the simple operation latency, equal delay stages. There's other things here too. I probably have in here someplace. So I'll just state them here. For RISC, a couple other things you wanted to do, because you had smaller instructions or less instructions, smaller instruction set. You wanted to have more general purpose registers on your in your CPU and your cores, and so you're doing a lot of simpler instructions and keeping the data close by and faster static RAM on the CPU in the registers. You also had an instruction format, fixed boundaries. So when an instruction came in, as soon as the opcode was being decoded, the operand fields would line up very nicely. And you can read about some of the other things that you can see here. The second thing we want to think about with performance is how to compute the time to execute a machine instruction with the specific contributions of cycles per instruction and the switching speed of the transistors and the number of lines of code in a given segment to get a certain task done. So this is a common paper that I use. I try not to have any overlap in any of my courses, but this is, I refer to this in different ways in different courses. I wrote this when I was a professor at Purdue University, an assistant professor, before coming to Elizabethtown College 21 years ago. And so let's take a look at this. This is some details you can take a look at, but it's not relevant to the performance. I'm just putting the whole paper inserted in here for the sake of being complete. Now here is the equation. So we want to take a look at that. And it's the time it takes for a task to execute. This is a machine instruction is equal to the average number of cycles per instruction times I sub c, which is the number of lines of code, machine code or assembly, because it's one-to-one with machine code, times lambda, which is 1 over the clock frequency to get the units to work out. And so that's your switching speed. And you can see there's a number of things that affect the performance here. So any kind of speed up measure is really what computer architects do, computer engineers inside IBM. This is what we were all about, was, for example, to reduce the average number of CPI was key. And so what we would do was a number of different things, including direct memory access between IO memory, superscalar, and multiple pipelines, multiple fetches at a time, hardware, all kinds of pre-actions. So cache is a type of pre-action, anticipate things, right? Temporal and spatial locality of reference, speed things up. And then also prefetching branches and virtual address translations or our branch history tables. If you branch before, you branch again. If you have virtual memory, which you almost always do because your address space is much bigger than your real space, so you have virtual addresses, you need to translate those, and then it pays to cache them. You also out-of-order execution, that was being pioneered at IBM, pioneered at one of my colleagues from IBM Germany, was working very close to me with what I was doing, and his whole thing was out-of-order execution, optimizing the instruction stream, and other measures too. So, and so you look at some of the details here. The CPI now breaks down into the number of P plus M times K, where P is the number of cycles for the instruction to decode and execute, right, in the pipeline stages, the number of machine cycles that takes to do that. And then M has to do with memory accesses per instruction. So we know that register reference, you don't have to do memory, go off of the core of the processor, across the front side bus if you're on a PC, and it's always slower to go out to the RAM rather than working right on the silicon. So, and then K is the ratio of memory access cycle time to processor decode and execute time. How much slower to get things from memory than to do things in the process. So that's the key concept there. So here we see an example of two tasks, and I'd like you to come back and take a look at this in detail. But what we have here is a comparison between a microprocessor and a microcontroller. So the microcontroller or the microprocessor was a very common Motorola microprocessor at the time. This was what was in the original Apple computers, and excellent architecture instruction set. Motorola was very good at putting together detailed documentation, textbooks. They even had a Motorola College in Schaumburg, Illinois. I debated switching when I came from Purdue to using their devices in the laboratory experiments, even though we used Intel microcontrollers. There is a whole family of microcontrollers inside of Motorola as well, the HC11s. But here we're comparing the Motorola microcontroller, the Motorola microprocessor in the first example to the Intel microcontroller. And so you just tell by looking at it, there's a lot more lines of code with a microcontroller, but if you look at the number of cycles that it takes, you can see it takes longer, even though you have these more powerful instructions, yet it takes longer for the microcontroller. So, take a look at that, and there's some other details on here you don't really need to look at for performance, but just give you a good general understanding. So, there's a certain task that's being done here, and it's showing in this example, the difference between the two. And then on the next page, this is the same example task, but this time it's doing memory accesses instead of just all the register accesses. So you want to compare the two because they're different devices. Recall that microcontrollers, different more registers, and so it's a good idea to ask yourself if you're packed full of memory references versus not when you're comparing. Is a microcontroller better than a microprocessor? Well, depends. Depends on the application. Depends what you're doing. So it's never a straightforward answer. This lecture is typically an advanced computer engineering course, but this same topic is also covered in another course called Digital Design 2, Assembly Language and Interfacing, where we learn assembly language, we program assembly language, and we implement things like this. In advanced computer engineering, typically you're creating a whole instruction set. After doing some device control things, you go into simulation and scale up. Here's just a little bit of discussion of CISC versus RISC. So the microcontroller is certainly always RISC. It's intentionally a small, simple device. It's supposed to be simple. Unfortunately, they scaled it up to Intel 8051 had only about 100 and something instructions, and then ballooned up to 300. They started putting new addressing modes and different combinations, how the operands work, and it, in my opinion, became less of a simple device. And it's a topic for debate. So you can read a little more there if you like. Just completing this paper here. This doesn't have to do with performance. This is just the beginnings of often the lab we do in 433 class, Engineering CS 433, Advanced Computer Engineering course. And the references that I used back in 1999 for this paper. So here's a little bit of computation, a little scribbly here. this, for finding your average cycle per instruction. So typically this was always in the back of the data books. Most things are online, but there wasn't too long ago where there were actually data spec books that you would look things up. And so the number of cycles is maybe given in several different ways, and it's changing quite a bit now. It's actually hard to even nail it down because of all the different things that could be going on. Or execution, multiple cores, certainly levels of cache was always an issue. So you see the number of cycles here can be expressed as a range with explanation of what affects the range. So cache hit and miss ratio, or you had to get it from RAM, miss. If branching, if you have a branch instruction, whether or not the branch is taken, right? Delays due to data dependencies between two simultaneous instructions in a superscalar process. You have parallel pipelines there, and you can have data dependencies between the pipes as well as resource or control dependencies. We learned about that in other parts of advanced computer engineering. So you end up with a fuzzy kind of number, but you get a range of numbers. You can somewhat nail it down. In the past, in advanced computer engineering, I've had students design their own instruction set, simulate it, and then compare it to the execution of an actual instruction set on a microprocessor or microcontroller. Even if they're just doing it by hand, it'd be better if they could actually do runs, simulation, and real-time runs, and find some way to normalize the data to compare it. Number two, the cycle may be expressed as a fixed number with corresponding deducts for events that slow down the processor, like a cache miss. So this was a traditional way to do it. Maybe a little harder to find that kind of data now because, again, there's so many variations of what's going on. But if you're designing computers and you are trying to reduce the number of cycles per instruction, well, you need to quantify and justify what you're doing. So this is not an uncommon thing to do. We did this kind of thing inside of IBM. And then this is just the same example rewritten down here with megahertz of the processor, from the paper above, and plugging in some calculations. So this is a 12.5 megahertz there. So, 1 over that to get your lambda. And then you have the number of instructions is 4, and a range of cycles there, right? An average, you compute your average. And then you just plug it in, and you see that you have a range of times from 1.44 times 10 to the negative 6 seconds, right? Microseconds to 1.6 microseconds. This chart we may have looked at before in advanced computer engineering, but it's good to look at it again here with performance. So the contributing things to what affect different parts of this equation. So the architecture, right, that those computer engineers control, and we did this inside IBM, that's instruction set architecture. The processor implementation and control for a given architecture. There's different ways to implement the same architecture. Certainly the cache and memory hierarchy and how that all works. Certainly in parallel processing, multiple cores and keeping cache coherency. When you have symmetric multiprocessing, you should all the cores and processing share in one memory. And then you see also compiler technology, and that's typically the computer science programmers, but it wouldn't hurt for all the computer engineers to take compiler design also. And so you can see this nice grid showing the different things. There's a little bit more you can read on here about throughput rate and workloads. We won't get into that right now. This is just part of the 8051 Intel microcontroller instruction set. Just a few of the instructions here, just to put one page in to give you an example. And you can see the number of cycles in the column over to the right. And so there's your times, right? Here's the Motorola. Here's just the excerpt out of the back of my Motorola assembly language book from long ago for 68,000. So again, you can get a look there, and you can read what's underlined there about affecting the times. This is a math coprocessor. You don't see this much anymore. This was when I was looking at neural network processors that I was developing on master's thesis in 1991. You typically had to do some of the mathematical functions, like for neural networks, the sigmoidal function. It's a transfer function inside the neuron. It's a trigonometric kind of function, yet you needed to go off on a math coprocessor to calculate. We don't do that anymore, but it was just something to consider. So here's the overhead of that. I suppose there's still math coprocessors out there someplace, but a lot of that's been integrated as everything gets packed in tight into the processor now, including multiple cores. Here's a simple PIC microcontroller. This is as simple as you can get with only, I believe, 32 instructions, just to show you that. Threw this in here because it seems relevant to just talking about timings. When you have a simple processor and it's not pipelined, it looks like the first diagram, but when you pipeline, you're doing multiple things at the same time. Now, that wouldn't really affect the metrics as much, but the superscalar does, the last one, because as we mentioned on the previous slide, you can have dependencies and two instructions both fetched at the same time. The out-of-order execution unit should be working so that it doesn't, so you don't result in data dependencies stalling the pipelines, where the one instruction is depending on the other, both executing at the same time. So if one depends on the results of the other, then you have one waiting and stalling. But it's something to consider. There's also resource dependencies and external devices, storage, things that can happen, or just RAM itself, actually. But, there's dependencies here, control data and resource dependencies. And so that's something to consider. The next thing we consider for speed up, for performance, is Amdahl's law for speed up, and then which limits speed up, we'll see, and then how to possibly overcome the limits on speed up that Amdahl's law states. So Amdahl's law is the computer engineering version of the law of diminishing returns, or law of diminishing marginal utility. Perhaps you've heard in economics classes. And simply put, the speed up of computer performance is measured in a measured way. However, you get less and less benefit for each incremental bit of effort you put in. So your speed up is going to be the time it took before you ever did anything to try to speed it up, divided by the new time, the reduced time, because you're doing some speed up measure, some hardware thing. And so there's that T old is the old time, and T new is the new time. And then the T new breaks into two parts, where you have only part of a given code segment is benefiting from the new hardware feature, and then a part that doesn't. That's the other. So there's two new. You have to account for both. So to plug in some numbers here, assume we have some code segment takes 100 milliseconds to execute, and a proposed new arithmetic logic unit could increase the performance of 40% of that code by 10 times. So what's the potential speed up of the entire computer? So the original time before doing any new hardware feature is 100 milliseconds. And so 40% of this is reduced by 10 in time it takes, right? We're speeding up. So we divide by 10. It's 10 times faster. So we're reducing the speed by dividing by 10 and the time by dividing. Increasing the speed, we're dividing the time, reducing the time. And then the part of the code that doesn't get any benefit is 60%, so that's 60 milliseconds, and the other, and therefore you add the two together. The new time is what part that benefit plus the part that doesn't, so that's 4 plus 60 is 64, and then you plug into the speed up of your original time divided by this new sped up time, and you get some number greater than 1. So that's that. Now here's a graph of what you can expect. Now, the very best with Amdahl's law you can ever expect is double the performance for the alpha of 100%. Well, Amdahl's law, actually, we're going to look at processors in a second. But this is just graphs here of the different percentages applying to that last problem. Different percentage of the performance contributed to the part of the computer due to the new feature. Now, what we really want to take a look at is this. It's the same graph, essentially, but we're now looking at numbers of processors or cores on the x-axis versus the speed up of the computer. And the alpha here is the percent of code that can be made parallel, applied in parallel processing. So, as you can see, the optimal here is double the speed for 2 cores, triple the speed for 3 cores. Now, in reality, unless you do something very unique, you're going to always have interprocessor communications. Your problems get parsed into pieces that get assigned to different processors, and then they have to coordinate, at certain points. Depends on the granularity of the problem, how much you can parse it, but you never expect double the speed with double the cores, double the processors, because there's always some overhead. And that's what Amdahl's law is trying to say here. So unless you do something unique, you will not have a way to overcome that. This is an article out of IEEE Spectrum magazine by the Institute of Electrical and Electronics Engineers, and it's named Breaking the Multi-Core Bottleneck. So before you take a look at this, you should understand Amdahl's law and the law of diminishing marginal returns, and how typically interprocessor communication makes it such that you cannot scale and speed up as you scale the number of processors or cores. You can't expect twice the speed when you have 2 cores and 3 times the speed when you have 3 cores. That would be the actual ideal situation, but because you have interprocessor communication, you have overhead to coordinate parsing problems and then coordinating the results back to between the cores. You're never going to have the ideal speed up. But that's the bottleneck that they're speaking of here. Now, what they found is they can actually surpass the ideal case. And so as you read here, I've highlighted in red a solution to one of the modern microprocessors' most persistent problems, the communication among processors in many cores. The answer that they have here is a dedicated set of logic circuits. They call this QMD, queue management device, that actually, as the number of cores is increased, the speed up became more pronounced. So they're breaking, they're going beyond the ideal case of Amdahl's law. So down at the end of this page, the QMD sped up sample tasks such that it looked like packet switching on the internet. So as you add nodes to the internet and you route traffic, like you can imagine traffic moving through a city, and you're optimally switching cars so that you have optimal throughput at each of the intersections on a giant grid. The more nodes you have with a given set of cars on the street analogy, you have better throughput overall. And so that's the idea, which is being applied here. You're taking internet routing protocol type theory, and you're applying it to the scaling of the number of processor or cores. So what you might want to do is take a look at an Amdahl's law graph and look at the ideal case, and then cases with non-ideal case, and see how the curves bend down, and ask yourself what the curve would look like here. And what's going to look like, it's better than ideal. The curve actually curves up. So as you add processors, you get more and more speed up. There's no law of diminishing marginal returns. It's, I guess you call it a law of increasing marginal returns. So prove to yourself that that makes sense. Compare and contrast this to Amdahl's law lecture, which we do when I deliver this this short little review of this paper. I always precede it with Amdahl's law lecture. So you should go back and forth, make sure you could understand and draw both of those graphs, both Amdahl's law, the ideal case Amdahl's law, the typical case where you have interprocessor communication and the curves bend down, and then draw and explain how you could have that curve bend up, where you don't have a decrease, but you have an increase in performance, an increase in speed up as you add more processors. And why that is, in words, is because you have, in this theory here, the equivalent of internet packet routing, where more nodes is better. And then you see at the end of this article, they say the Intel engineer, this is by Intel, involved couldn't comment on whether this would find its way into future processors. So this is a theory. I haven't seen it yet implemented. And so when you're, if you're doing a PC design in 2020 as your midterm exam, one of your second midterm exam, don't expect to see this in a processor. Don't look for it, or don't be sad if you don't see it, because it's a theoretical kind of thing. Now this is from 2016, so I have not seen in the latest processors this being implemented yet. Maybe there is one, but don't expect to find it, and don't be upset if you don't when you're trying to design a PC with technology that is in the marketplace at the moment. This fourth method of looking at performance is somewhat of an academic exercise. We never did this specifically inside of IBM. We definitely did the other four things that we're talking about here with performance. But this is something you will see in advanced computer engineering textbooks. And so what we're looking at is looking for the computing the average parallelism, both in the discrete way, where we're adding up little parts, versus using integration, the continuous way. And then think about the discrepancy between the two. So here you see an example of discrete versus continuous. And this, if you are in engineering and you do signals and systems and control theory, you know that you can do things in both continuous and discrete time. Although probably in undergraduate education, you're just looking at continuous time and control theory. But in signals and systems, you should be looking at both discrete and continuous. So in discrete time, you're talking about time series. In continuous time, you're talking about integration. And it's just as you could imagine, you're chunking it into little blocks that you're adding up if you're doing discrete time. And in integration, you find the limit as the slivers get smaller and smaller. So this is just looking at that and that example, or this particular example. So take a look at that and make sure that makes sense to you. And we're continuing this, and talking about the relative error between the two. And if you like mathematics, just a little refresher on integration, the area under the curve. So an integral, you can see the little slices that you take. There's a part, positive error, negative error. And how that would look over curve. And then some examples with limits, right? And take a look at that. And then, this is the derivation of an integral here. It's the limit. You go to infinity, your slices get smaller and smaller, then your error is going to go away. So that's just a fun little exercise. And our fifth way of looking at performance is common benchmarks for consumers and information systems, people ordering machines, maintaining machines. We did do this inside IBM, called a burn-in, where we would run for 3 days the $1 million machines, the instruction mixes. But in general, when you're designing a machine, you do all the other things that we had talked about, of more, maybe not so much mathematical models, but certainly the other things. And so this is a very nice website here for looking at a number of different things. Firstly, the CPU performance. Then they're looking at video cards, right? And so you'll probably recognize some of these. The gamers will, certainly. And this is the 3D mark, which is one type of way of measuring performance for video cards. Also the direct compute operations per second. Then they evaluate disk drives, hard drives. They evaluate RAM. DDR4 is, at the time of this evaluation, the fastest double data rate. Memory access on both the leading and trailing, right? The rising and falling edge of a clock pulse. Learn about that in memory lectures. This slide is for read, uncached read access. And then writes with DDR4. And then finally they rate here 10 top systems in April 2020. And you can take a look at that and how that graph things have changed over time. And a couple common performance standard from long ago. If you drill down into the instructions per second, machine instructions per second, and also floating point operations per second, right? For your high precision scientific notation, binary floating point, double and single precision that you need for your multimedia and streaming and audio and video. And here is a website, and some discussion of some machine learning metrics and how you would measure those. And you're welcome to drill down into that if you like. We will not discuss that in this particular presentation, lecture.